So yes, let us backtrack a bit. So since I got some questions in the break, so we have that the error at En equals Un minus U of Tn, right? So this is from your numerical solver. So it's a numerical approximation. And this is your true solution. Like so. So the way to distinguish them is that you see this has the parentheses and this just has the subscripts. And then to reiterate, yes, we are proving that it's convergent here. So there was maybe some more lines. So we already proved that Euler was consistent. This means that, let's see, it's consistent. We prove this because lim delta t tau n, no, just tau basically. So that's a local truncation error. And the local truncation error, well, E0, this is your first time step, so this is equal to the first truncation error, which you know is 0. So then this disappears, this becomes 0, like so. And you are left with, well, En is less than E t lambda 1/2 delta t tc, which goes to 0 when delta t goes to 0, like so. So then we've proven that, well, it's consistent. That's easy. We've used the proof of consistency in proving that it is convergent, and since it's convergent, it's also stable. Right? So if we write this equation, so consistent plus stable is the same as convergent. So what we've done here is, first we have proved that it's consistent. That was easy. We've used this to prove that it's convergent, and when it's convergent, well, then we know that it's both stable and consistent, so then it has to be stable, which follows from logic, hopefully. I mean, I don't want to be, it's a philosophical debate about logic. And yep, so this is for ODEs. So we can look at partial differential equations, but I want more space. So this should be okay. You've already noted it. This is also a repetition from earlier. And that's the result. Yeah. So for PDEs. So the local truncation error is defined similarly. So we'll have an example where we will look at the diffusion equation without any, well, sometimes called the dimensionless diffusion equation, because you don't have any scaling here. Xt. So if we use an explicit method, we will have that u, I, n plus 1. So n here, this is time, this is position. U, n, I plus delta t over delta x squared. U, I minus 1, n, I, n. U, I plus 1, n. So then we see that the truncation error for this is x of t, u, t, no, x, is it? Yes. X. So here you see I'm using the exact solution as well. T minus ux t over this step length delta t minus 1 over delta x squared u x minus delta x of t minus 2 u xt plus u of x plus delta xt, like so, I guess. So first we can check for consistency. Let's see. So consistency, well, this is easy. You look for lim delta x and delta t both equals to 0 of the truncation error 0. The next, well, if this is 1, then the next step is to show stability, because it shows that for PDEs it is easier to show first that it's consistent and then show that it's stable, and when you have these two conditions you will have that it's convergent. Show stability. So we'll look into how to show this stability. Stability T. So I just assume that we can actually show that it's consistent now. It shouldn't be too hard to calculate. Convergence follows. So to show that this is stable, we have to take a detour looking at von Neumann analysis. Or VNA. So VNA is based on Fourier analysis. If you remember your 4K, or 4, math 4 anyway. So just briefly repeat. So we have that the Fourier transform f of a function small f of x. I will denote this with f hat of xi equals the function multiplied by some kind of exponential xi, and then it's dx. And the most important bit here is that if you take the Fourier transform of a differential, let's call it f still, f of x, you would then just get, see, this, the Fourier transform at that point, and just some kind of constant. And I here is the imaginary number. So now it's not an iterator. So now it's the square root of -1. Yep. So we could say that by using this, we see that e to the power of I xi x is an eigenfunction of the differential operator. So this. Differential operator. Partial x. So you have that dx I x equals I psi. So this is similar to, you have a x equals lambda x, where this is the eigenvector, no, not eigenvector, but eigenvalue of this matrix A. So you see, instead of doing this operation, you can just have a scalar value. So it's similar. It just has fancy words. So we'll also introduce a grid function, which is, see, I think I call it Vn. So I'm going to introduce this grid function W n equals E I n delta something, in this case x xi. So this is an eigenfunction. Eigenfunc of all the finite difference operator, of all or any of the operator. So a lot of fancy words. So I'll show an example of this. So if we just have the central difference, which is d0, working on this w, and have delta x e I n plus 1 delta x xi minus e I n minus 1 delta x xi. So this can then be rewritten such that we have e I delta x xi minus e minus I delta x xi, having the eigenvalue I and delta no, not eigenvalue, but see this I over, so we introduce I again here, the sine of delta x psi ei and delta x psi, and we see we have I delta x sin the sine of delta x psi w n, like so. So this might seem like a crazy step, but if you look at the definition of the sine function, you see that this is actually true. So in this VNA analysis, we'll do some assumptions. Just to make it easier. So we will assume that we have the next CM M I delta x, and then so if you assume this, then it can be proven. So this is going to be some hand waving. Unfortunately, it can be proved that, see if we get this correct this time, U, so the Fourier transform of U, m plus 1, second norm, is less than 1 plus alpha delta t of 2. So if this holds for some kind of constant alpha, yes? Oh, yes. Is it down here or up here? Yeah, sorry. I was thinking about it, but just a constant. Yes. So if this holds for some constant alpha here, then let's see that I say this correct thing. So yes. So if this holds for some alpha, then you prove that it's stable. So we can utilize the Fourier transform to get a so-called recurrence relation, which means that each of these U of n is decoupled from each other, meaning that we can get a formula of the form. So by using the Fourier transform, we can get that U of m plus 1, 2 norm of this is less than some kind of function of psi U m2. So then we will look at this function here. So I'm sorry, but this is some kind of hand waving. Which is to say that you don't need to know the details behind this, just that there is some function g. So if you can now show that using this function g, psi is less than or equal to 1 plus alpha delta t, well, then this holds. So if this holds and this is true, then this holds. So then we're all set since, let's see, no. Since then we have that u m plus 1 of psi should be less than plus alpha delta t u and xi yes, so here it's only the absolute value, which means that the 2 norm u m plus 1 of psi up to is less than 1 plus alpha delta t 2 norm n. So if this holds, then this should hold. So we'll focus on the one there. Yes. So how does this g function look like? Let's try with an example again. So right now I look at u t plus a u x equals 0. So we'll have a finite difference method here. And please correct me if I'm wrong. N plus 1. I'll use a central difference. U of, I guess it's going to be m here, minus 1j, so my notes are wrong, plus 1, no. A delta t over 2 to x j plus 1 m. Yes, this is should be minus here, I guess. No, I think so. This does make sense. But we assume anyway that this can be written on some kind of form u of jm equals g psi m, and now this is to the power of e I is j delta x psi, like so. So this is a power. So this isn't an index, this is actual power of. Yes. And inserting this into the finite difference method, we should get, yes, I see this is wrong. There should actually be minus 1 and plus 1 there. See that g m plus 1 I j delta x psi g of power of m I j minus 1 delta x chi, no, psi, sorry, power of m I j plus 1 instead of minus 1 delta x shy, well, minus a delta t over 2 to x g m I j plus 1 delta x chi, and again m e I j minus 1 delta x, like so. Not zeta, but psi. So we can solve this for g. Let's see. G of psi should be equal to 1/2 e I delta x psi plus e I delta x psi minus a delta t by 2 delta x. Then we have this thing again, e I delta x psi minus I delta x psi, and then we can use the same relations, and let's see, this is a half, should get the cosine of delta x psi minus I guess just cancels, delta t over delta x sine of delta psi, like so. Then you see we have the cos and the sine. So if we square this, I'm going to do this over here. Then we'll get a neat trigonometric function. So we're doing a lot of tricks here. Squared as well equals the cosine squared of delta x psi plus the, well, I'm gonna have this in front of it, so a delta t over delta x squared sine of delta x psi, and again we require that this should be less than, let's see, g of psi should be less than plus alpha delta t from earlier, but we're just going to ignore this and say that this we're going to look for is less than 1. So if this g function is less than 1 and both of these are positive constants, well, then this is a stronger inequality than this. So if you just look at this and don't make any assumptions, we see that we have, well, I mean, the cosine squared plus the sine squared equals to 1. So we're only interested in this bit. So we see that this relation holds if a delta x over delta t, absolute value of this, is less to and equal 1. You see why? I mean, because we have that cosine, well, I'm going to do theta plus sine squared theta equals 1. And since we only can do something with this, well, if this is less than or equal to 1, if this is 1, then you would have the same as down here, and this would be 1. But if this is, well, less, then it says the reason that the sum is less also. Yes, it should be sine squared as well. Like so. Yes, because you square all of it. So I mean, it's the same. You basically have the length of this, because this is a real value and this is an imaginary value. And the square of this will just give you the, or the absolute value will just give you the length of that vector.
So why do you require that the g of psi is less than or equal to 1?
Ah, this? Oh, below. Oh, yes. So if this holds true, so this is a stronger inequality than this. So if this holds true, then this holds true. So I'm just going to ignore this random constant alpha and just say that, oh, I'm just going to focus on this. So maybe this could be a bit above 1, yes, but if it's less than 1, then you know that it's going to hold. So it's better to be safe than sorry, as the saying goes. So do you think you're able to perform this for the project? I mean, if you cite it correctly, then you can get these stability criteria. I mean, you're not supposed to derive it yourself, but if you want, then you feel free. But I mean, I've already given stability criteria for both the diffusion equation and the wave equation. So you can just use those. So then I have a couple minutes left, like 10 of them. So we can talk about the project. So, please read the full project text before you ask questions, as there's a lot of details in it. The main thing to think about is that you should have a maximum of 12 pages. I think it says, well, down. Anyway, so this is mandatory. If you do not deliver a report, then you can't take the exam. Meaning that you can actually submit a empty report and still take the exam, but this is still going to count for 40% of your grade. So even if you score a full score on the exam, you will only get a maximum of C because you lack 40%. It's mandatory, and there's some guidelines you really should follow. So you need an abstract, a theory, implementation, results, discussion, conclusion, and references. That is the basic structure of a report like this, and the report should be a self-contained document. So you have to imagine that you don't have this project text available, and you should try to motivate your own research or the report or the work you're doing. So this is just basic guidelines. Yes? Yes, you can have appendices. That does not count. I think that, yes. So the maximum amount of pages allowed is 12. So this is excluding, for instance, your code, because the code takes up a lot of space, and derivations, extra information, etc., whatever you want. So if you are very proud of your, well, the formula derived, then feel free to add it. But it won't affect your grade that much. The code, though, that will affect your grade. And you have to deliver it in PDF format. That should be possible for all of you to do. So if you do not deliver it in PDF format, it will not work, and you will actually fail the project. So, but this should be a pretty easy requirement. And what will be considered during the evaluation is the methods you've used to solve your problem, how you write your code, that it's actually possible to write your code, that you use variable names that make sense, and it's not just a big jumble of, well, mess. We will also judge you on the language you use in the report. You should write clear and concise English or Norwegian. Also plot quality. So I don't want a 20 by 20 pixel plot with no labels or anything, because that doesn't make any sense. And you should also consider, do I really need this graph to be in 3D? Does it convey the same information if it's still in 2D? A good function to use there is just image scale. So image sc of your function. I mean, it gives you a 2D view of your problem. So instead of having this surf function, so you have like this fancy 3D graph, this one can actually give you the same information because you have a third dimension in color. Only that you can actually see everything. And also the layout of the report. So again, I really recommend you use LaTeX because, well, if you do the plots correctly, then it's easy to get the plots in there, and it's easy to reference all of the figures and equations and whatnot. And also the layout, it's easy in LaTeX. You don't have to worry about the layout, you just write text, and then it is compiled for you. So I have two problems for you to solve. I've called them problem alpha and beta. So in problem alpha, you're supposed to solve the wave equation. That means both the acoustic one and the elastic one. So we haven't really solved the wave equation, have we? But you're supposed to solve them in 2 dimensions. And this seems complicated, but it's basically just a system of linear equations. So if you just look at this and think for a bit, you should be able to implement this. And of course, you're free to use Google and collaborate. Just don't steal each other's work. You have to write your own code and report for a group. I guess I forgot to mention that, but you can work either just yourself, or 2 or 3 in a group. So maximum 3 people in one group. But you are, of course, allowed to collaborate, but not plagiarize from each other. But yes, the wave equation. It summarized some of the things you have to worry about. That actually the acoustic wave equation, which was more commonly used before in, for instance, seismic exploration, it's only valid for fluids. So when you send or knock on a table, you have more than just these pressure waves that the acoustic equation can describe. You also get something called shear waves. So it's a more complicated system. So you get actually more information. So a interesting topic, well, I'll actually include models as well first. So this is the Gullfox field. It's a model of it. I've only plotted 2 of the parameters here, but when you want to work on the elastic wave equation, you need 3 model parameters. One of them is the density, the other one is the p wave velocity, and the third one, which I didn't have space for here, is the s wave velocity. So these are all contained in an attachment. You will find both on Slack and on Blackboard. And we also have this recur function in order to create your wavelet you should use. Boundary conditions for the wave equation isn't really that important, but you should try to think about what does it mean to not have any boundary conditions in the wave equation. And I guess if you're under simulation, you will kind of figure this out by yourself, what it means to not have boundary conditions in the wave equation. And I've just listed, I think, 2 interesting topics. So that is to look at the effect of using the elastic wave equation as compared with the acoustic wave equation. Actually see that you get more information by the subsurface. And also you can try to play around with where you want to place your recorders. Do you want to place your recorders on the sea floor, or do you want to place it in the water? So water is a fluid, so shear waves won't travel in water, so you maybe you will lose some information there as well. I mean, you do have SP wave conversion at the sea bottom, so you will get some extra information if you use the elastic wave equation, but maybe it's better to actually place them on the seafloor. And you can also play around with which kind of parameters they are supposed to record. So that's one of them. And then problem beta is the 2-dimensional diffusion equation. So again, this is just pressure. I've provided a model of it looks like zebra stripes, so you're not supposed to use this model if you don't want to, but it illustrates a porous network. And then you can see how the pressure is distributed inside this porous network. But for both problems, it's best to just look at homogeneous models first, so you see that it works. So actually a problem with using this model is that you have to have boundary conditions for all of these blobs, which might be hard to figure out. But by using the edge function, you should be able to get the edge of all of these shapes and actually apply boundary conditions here, because these should be non-permeable regions. So if you don't do this correctly, then they will just be 0 pressure regions and basically suck up all of your pressure that you apply to it. And for this problem, the boundary conditions, as I've kind of sketched, is important. So if you pick problem beta, then really look at the boundary conditions and what I mean in a physical sense. And some interesting topics. For instance, you could see what happens if you try to clog some of the pores. So some research is being done that, for instance, I guess water would flow through the larger pores here. Oh, and you're not supposed to use two-phase flow. That's too complicated. That's how you would do it, but you can kind of get an estimate of how to do it. So yes, so the water would easily flow through here. You can look at this from the pressure gradient. And if you have some oil down here, it won't come loose. So if you try to plug this pore, either by injecting bacteria and nutrients for them so that they form some kind of mold that clog the pores, or if you could actually invent some kind of nano gel or something that perhaps is shear activated. So when you have a lot of shear in this, then it will, I don't know, break apart and clog the pore. Anyway, the method of actually clogging the pores isn't really that important. Important stuff is that you have this kappa, which changes over time, and see how this affects the system. And then you can introduce, for instance, a dummy variable, which is the oil content inside your porous network, and have this be affected by the pressure, for instance. And common talks for both problems is that, well, you should perform a literature study, so you should see where your equation actually used in the oil industry. And for this, Google Scholar is a great resource. And then you're supposed to implement a 2D numerical solver for your problem in finite differences, so not finite elements. Actually, if you do it in finite elements, that is actually fine. And you're free to use whichever programming language you're comfortable with, although the student assistants are mostly fluent in MATLAB. Again, most of the differentiators I presented are fairly simple, so I encourage you to try to have larger differentiator operators by using the theory we've gone through, or you should argue why this simple operator or this short operator is enough to solve your problem. You should interpret the physical meaning of your boundary conditions or the lack thereof, meaning if you pick the wave equation and you don't have time to implement boundary conditions there, then you should ponder the physical meaning of not having boundary conditions there. Investigate the stability of numerical implementations. Again, you can base yourself on available literature and, well, just experiment with your solver, basically. First, you should perform simulations on homogeneous media, because that is easier. You can actually try to figure out the analytical solution in your homogeneous media as well and try to compare with your solver, see if it's actually as accurate as you claim it to be, or maybe it's more accurate that you claim it to be. And then lastly, you're supposed to create an interesting problem. So for this interesting problem, you're completely free. It should just be based on your equation. So the topics I've listed, those are just suggestions. But if you figure out something that you want to investigate instead, then feel free. I see that I'm out of time, so just briefly summarize. I have some guidelines on how to write scientific reports and how I would prefer the communication to go. So I mentioned this at the start of the lecture, but I would prefer if you do not send me an email and rather just ask in a public channel on Slack. Because if you are wondering about something, I'm sure someone else is wondering about the same thing. And the meaning with Slack is that it should be a low threshold contact point, so you should just have a conversational tone. You don't have to greet me anytime, every time and use titles. I mean, it's a public channel, so it's supposed to be convenient for you to use. Just ask. As I mentioned, you're allowed to deliver the report in groups of 1 to 3 people and also collaborate, but do not plagiarize from each other, because we will run a plagiarism control, and if we see that it's basically just plagiarism, then you're not allowed to take the exam. So please be wary of this, because I've had trouble with students just copy-pasting from the web. You shouldn't do this. I mean, you're allowed to use it as research, but you have to write it in your own words, paraphrasing. And then share LaTeX in GitHub or Git is recommended for easy collaborations. So you can have a look at those. Any questions, like right off the bat? The deadline. The deadline is in 30 days. So the 12th of November. Since this month is 31 days. Yep, and the TAs, they will be available in the regular hours in both October and November. Task with this. Yep. No, there's no lecture next week, as dictated by the. So there's a information